Hello guys. Okay, so in this session we'll be talking about what we did in lecture 5. So we're doing permutations, combinations, and counting techniques. Okay, so let's just start. Now we'll start with the counting techniques, and then he said the branch of mathematics that deals with counting. It's called no actually this combinatorics. Yeah. So anyway. Okay, so we have simple. So the three major counting. I left one out. I left one out. But then the three major counting techniques is the multiplication rule, permutations and combinations. Okay. Now we'll start with multiplication rule and then see what it's all about. Okay. So for instance, with multiplication rule, it's just a counting technique. You're not trying to pin down on something. You're just trying to see what are the possibilities. What is this like? What is the sample space available? Okay, so that's all you're trying to do with that. So let's say there's an example in the slide where a student tosses a coin and rolls a die at the same time. So how many possibilities are there? You know that a die can give two possibilities. That's head or tail. And then a coin can give six possibilities, so 1 to 6. Now you won't say that because this has two possibilities, 6 possibilities, you add them. It's actually the multiplication rule. That's why it's multiplication. So you just simply multiply them 2 times this and you have your 12 possibilities, and then you can actually draw that out, right? Now another one, let's say so you put another example in the slide. Some guy has 12 slugs, 3 shirts, 2 shoes, and then 5 ties. So in how many ways can a person dress? And he just multiplied. Or maybe how many outfits does a person have to choose from? You just multiply everything, right? Okay. But then let's try a simpler technique that can be. Let's see if it will be more practical. So let's say you have. Okay, so let's say you have 3 pens, right? 3 pens, say 2 books. Okay, and then what? Okay, so let's say 3 pens, 2 books, right? And then we want to find, basically, you want to go for a seminar or something. So what are the possibilities of how many possibilities are available to you to pick a stationery, right? I'm just limiting the stationery to pens and books. Okay, so what would be your possibilities? So for instance, let's say you have, so that means that you will pick either your first pen, right? So let me label your pens for you. So let's say your pens are called A, B, C, and your books are called what? Let's say X and Y, right? So in multiplication, what you're simply trying to achieve is that it's either you pick pen A, right, and then book X, or you pick pen A and book Y, or you don't pick pen A but you pick pen B, book X, pen B, book Y, or you pick pen C, X, Y, in that order. So by the end of the day, you can choose one you take for the program, right? So you need 1 pen and 1 book for the program. So you have how many possibilities? 6. So it's just like saying it's the product. I hope this makes sense. Okay, so moving on, let's talk about something. So if they give you any of those questions, you just multiply and you have your answer. Nothing big. Now let's move to permutations, right? Permutations. Now permutations. Okay, so when you mention permutations, you also mention combinations because they are really related terms. Yeah, and then well, if you're interested, but then the history of permutation and combination really starts from very far back in somewhere the 16th century, like early 16th century, where Cardano, some guy they call him Cardano, He was a mathematician, European mathematician. We have Blaise Pascal, the popular Pascal guy, Jacob Bernoulli, and then Euler, Leonard Euler. So there are some of the pioneers of the whole field of permutations and combinations. Yeah. So that's with that said, let's move on. So we have permutations. When you talk about permutations, you are trying to perm things, right? You're trying to perm things. I don't know if that's a word, but yes, it sounds like a word. So you're trying to arrange things, right? So order matters. Yeah. So that's just order matter. It's just like this is a bad example, but then anyway. So if you are plaiting your hair, some I think there are hairstyles you call perm. But then one simple thing you can use to remember that in the earlier stages I used to remember was if you are plaiting hair, it matters the order you pick each of the row. So they divide into three. So it matters where you pass each of them, right? So your order matters. Oh, but that's a bad example though. Okay, so um, let's pick something here. So let's just get to the general formula for permutation. But then before that, there are two kinds of permutations you can know. Right. So you should know that there are permutations where repetition is not allowed. Right. And there are permutations where so where it's allowed and then where it's not allowed. So those are your two kinds of permutations. So for instance, let's say you want to pick password for your phone, right? So password something. So you can decide to pick your password as 2222. This is allowed, right? But then you have four people on the field, maybe athletics, right? So one person cannot be first and last at the same time. Yeah, so that's just the idea of permutations with repetitions. But some of them are actually repeatable. And then there's the proof for it. So maybe I can make another video for that. So that we just use this video to concentrate on the major thing you should know. Okay. So calculating permutations and permutation R. So, and then this is your formula. Okay, I don't know the format of the exam. I don't know if it's going to be objectives. But if it's going to be objectives, you don't even need to do this. So you just find your numbers. So let's say you have 8 things you are trying to arrange it in. Let's say so you find your permutations here, right? So you find your permutation here and your combination here. So you can just do maybe 8 combination permutations here, this, and you get yours. So yeah, so that's just it for permutations. But then if you want to solve it the analytical way, this is how we solve it. So let's take an example where we have 5 things and we want to arrange them in 3 different ways. So that gives us 5 factorial over 5 minus 3 factorial. So that gives us 5 times 4 times 3 times 2 times 1. All on that gives us 2 times 1. Okay. Then you can always have this. So you always have like something easier to deal with. So this is kind of a more moderate example. And let's move on and see if we find other interesting examples. So we have something like a combination lock will open when the right choice of 3 numbers, that's from 1 to 30 inclusive, is selected. How many different lock combinations are possible, assuming no number is repeated? So if you are doing with a repetition, then it's directly your 30 factorial over 30 minus 3, right? Because you are trying to get 3 numbers. So that'll be like 27 factorial. And then you can always do 30 times 28 times 29, right? 29 times 28 times 27 factorial. Then you cancel out the factorials. Yeah. So you have this. So what this simply tells you that, well, if there are no repetitions, right, then you have that. But if there were repetitions, how would we solve it? If there are repetitions, then I'm thinking that it will be, so your first time you have 30 options available to you. Your second time you can repeat it, so there is still 30 available to you. And your third time you can repeat it. So it will look like a larger number. So that's just how to solve. So this one will be with repetition and no repetition. Yeah. So if you're doing repetition, it's just like the same product. Okay. Um, okay. So we have one example about choosing 5 people for presidential positions. Okay, for executive positions from 25 people. Basically the same format. So you just take n factorial over n minus r factorial. Okay. Okay. So basically that's just it for permutations. There are other forms of permutations that we didn't consider. I don't know if you bring them in there, sorry. Yeah. But then if it doesn't, then that's fine. Because since you didn't mention that. But then we have things like cyclic permutations and all of those things. So they are all different types of permutations that you can work with. Yeah. So if we had maybe cyclic permutations, then we'll have to solve it in a different way. But then since he didn't mention it, we'll just continue. Just continue what we have in the slides. And now let's get to combinations. So in combinations, what are you trying to do? In combinations, you are trying to do selection. Yeah, so combination, you're trying to select. In permutation, you are trying to perm or you are trying to arrange. Okay. Yeah. But then take note that sometimes the language changes. Maybe in permutation, you find a permutation question that says, in how many ways can you choose arrange? But then mostly it depends on how they say it, right? Yeah, it depends on how they say it. But then when you find most questions with choosing, then it's most likely a combination question. And in combination, if you are choosing something, the order does not matter. So n combination r simply n factorial over r factorial times n minus r factorial. Okay. Let's just see if we get some examples. Okay, and then the same thing for combinations. You can have repetition and the one without repetition. All of those are possibilities. Okay, so we have an example in the slide. So it says that how many committees of 2 chemists and 1 physicist can be formed from 4 chemists and 3 physicists. So you have 4 chemists, right? 3 physicists, and then you want to find the ways to choose a committee with 2 of this, right? 2 chemists, so 2 chemists and then 1 physicist. Okay, so now how do you do it? So that means with the 4 you choose 2 times, with the 3 choose 1. So that's all. And then so this one you can just put in your calculator and get your answer, or if you want you can just calculate it. So that would be like 4 times 3 times same thing, right? Times 3. So that gives you, oh wait, okay, yeah, I think I left out something. So 4 times 3 around 2 factorial, that's simply 2 and 2. Okay, so that'll be yeah, so that's just simply the same thing. So this one gives you 2, so this one gives you 3. So you get 2 times 3 times 3, that's 18. Okay, so this okay, let me see. We have another question. A student must answer 3 out of 5 essay questions in a test. In how many ways can the student select the questions, right? So that's simply 5 combination theory. And then there are ways you can just solve this. 5 factorial over 3 factorial, right, times 5 minus 3 factorial. You can simplify this thing. Okay, yeah, so there are quite a lot of examples in the slides with solutions. I'm trying to see if I find something that doesn't have solutions so that we can try it out. Okay, so what's the difference between permutations and combinations? So both are possibilities. Okay, well, we know that both are possibilities of counting, right? So they are counting techniques. Both are counting techniques. And the only difference between permutation and combination is whether the order matters. So you can write one equation that relates permutations and combinations. Look at their formulas. So we know that n permutation r simply n factorial over n minus r factorial, and then n combination r is is n factorial over r factorial n minus r factorial. So this tells you that your n combination r is the same thing as your n permutation r on r factorial. So you find that they are really related. So when you the r, this one is this one determines whether order matters or it doesn't matter. Yes. Okay. Okay, so that's just it. And then we have the combination formula proof too. That's quite long too, so we can do that in another video. And we also spoke about corollary, or is it corollary? How you pronounce it? Okay. Okay, so that was just it. So let's move to one of the last things he mentioned on the slides. So we're dealing with so that's fine. So the last thing we're dealing with is so he went more into permutations, right? They're trying to arrange. So let's just say we are going to solve questions, right? That would be better. So let's solve questions. So one is, let's say you are given a word like success, right? So in how many different ways can you arrange or reorder success? So there's one question, but then so you know that there are some similarities, right? Because some of the words, some of the letters look like each other, right? I mean, some of the letters are the same. So if you are to arrange this, right? So n permutation r for this particular case where you have repeated items, then that will be n factorial over repeated item 1 factorial, their number, repeated item 2 factorial, in that order. So now let's try on this example. So here we have 1 2 3 4 5 6 7. So we have 7 factorial divided by repeated items. What's repeated? CC. So 2 factorial times SS times 2 factorial times what again? That one also is repeated. Okay. So okay, S are even 3. Sorry. So that will be times 3 factorial. And then you'll be left with 1 last. That's 1 factorial. So you can leave it out. It's not necessary to add. So you can just say that will be 7 factorial and 2 factorial times 3 factorial. And then what would that be? You can always type that into your calculator actually. And then just in case you don't know how to type factorials, which I'm sure everyone does, you can just type this way. Alright. Then you get 420. So you get 420 ways of arranging this. And then we can pick other ways and then do the same thing to them. So let's say, okay, he gave an example like Mississippi. How do I spell Mississippi again? Okay, so this Mississippi, and you want to arrange it. So 1 2 3 4 5 6 7 8 9 10 11. So that will simply be 11 factorial divided by number of common terms 1 2 3 4 factorial times how many p's? 1 2 2 factorial times what's repeated again? 1 2 3 factorial. So you can just do this and then you don't have to waste time on these stuff, so that you get more time for something else. So 4 factorial times 3 factorial times 2 factorial. So you get 138,600 ways. That's quite a lot. And we have the same thing for abracadabra. So you can always try those ones. Okay, so moving on, there are quite a number of examples in the slides. Okay, so we'll just brush through some of them. Some of them will not necessarily solve them. So we have one about selecting someone for UN, for a UN council, and then it's literally straightforward. So just, but then we'll solve some of these ones and then send to the groups. And then we have a Venn diagram question. So you can either decide to go with the Venn diagram approach or permutation and combination approach. Okay, there's one about, so it says that if there are 4 Czech tennis players, 4 US players, and then 3 Russian players at the US Open Tennis Championship, how many ways could they be arranged? So if you are looking to arrange these people, then you should know something about the game, right? So you should know how, whether they play with 10 people, they play with 11 people, or whatever. So yeah, so you should know all of those details to do the arrangement. So let's say, well, I don't know much about the game, but then let's say if there are 11 people who are going to play, right? If there are 11 people who are going to play, then you can simply do 11 factorial over the like terms, the number of like terms. So there are 4 like terms for Turkish people, there are 4 like terms for US people, and there are 3 like terms for Russian people. So it's just this, right? But then once again, it depends on the game. So if the game has a different number, then you calculate it that way. That's just me thinking. Yeah, so you get something like this, right? If you assume that you are playing with 11 people on the field, that's the, and then yeah. Okay, so there's another question in the slide that looks a little interesting. So it says that show that n is positive, n is a positive, show that if n is a positive number integer, then 2n 2 minus 2n2 equals n squared. Okay, so this is an interesting question. So we can solve this. Right? So let's solve this and we move on. So 2n combination 2 minus 2 times n combination 2 is n squared. Well, we don't know yet, but then we can prove. So how do we prove that? Then we say 2n factorial, right, over 2n minus 2, right, 2n minus 2 all factorial times 2 factorial, okay, minus 2 times, so just be careful to not put the 2 inside anything, n minus 2 factorial times 2 factorial, all is equal to n squared. So from here, what can you do? Okay, so from here you can start eliminating some of the terms. So you can eliminate this. So let's see how to eliminate that. So you get 2n times 2n minus 1 times 2n minus 2. Oh, sorry. All divided by this 2n minus 2 factorial times 2 factorial minus the same. We can do the same thing for this. Then we can do n minus 2. Okay, sorry. So we do n minus 1, n minus 2 factorial, all divided by 2 factorial. So I guess you understand why we are doing this. So we are just trying to simplify now to prove that this side equals n squared. That's all we are trying to do. So this simply goes off with that, and what again? Okay, there's a factorial. This goes off with that. So we end up with something interesting. So we get 2n times 2 minus 1, or minus, okay, divided by 2, or minus 2 times n minus 1, also divided by 2 factorial, of course. That's good. Now we can always get rid of this, then we get 2n squared minus n. Then we can get rid of this, then we get minus, right? Minus, what do we call it? N squared minus what? N squared minus n. So you find that, brackets. Okay. So you get this, okay. So let me just expand it so that it doesn't look like I'm making things. So you have 2n squared minus n squared plus n. Then this goes off with that, and then when you subtract this and that, you just get n squared. So that's just it for this formula. So we've proven that this. So we've proven that this is correct. Yeah. And then these questions can come in any form, right? They can give it to you in any form. Okay. And then there's a last question. Let's just tackle the last question, and then we'll be at par with everything. Okay, I'm running out of sheets. I'm coming. Okay. Okay, so let's get to the last thing. So it says a witness to a hit and run accident tells the police that the license plate of the car in the accident, which contains 3 letters followed by 3 digits, starts with the letter AS and contains both 1 and 2. How many possible license plates can fit this description? So you have a crime scene where the one who saw whatever happened does not remember everything. So the person remembers that the license has AS, but then they are saying that you're supposed to have 3 numbers followed by 3 digits. So you are supposed to have, let's say, some 3 alphabets. Let me just say 3 alphabets, and then 3 numbers. And then the person remembers this, and the person remembers that it contains 1 and 2. Interesting, the person didn't even say the order of the 1 and 2 it was, right? So let's say you are a police personnel, which you are not. But then if you are trying to analyze how many different license plates can fit this description, so you are trying to weigh your possibilities, right? You are trying to weigh your possibilities. Which people can you contact? Which license numbers can you put as your suspect list? Okay. Then, so here is, so in this thing, arrangement matters, right? Arrangement matters. Now, what you know is that it starts with AS. Now, you don't know the third thing. So there's something that's missing here, right? So how do you find that? How do you find that? So to find something that would fit here, you know that there are 26 alphabets, and each of them, so just in case they said that probably some letters are not, so if the police have further understanding that some letters are not in the number plate, then they can take those ones out. But for now, we can just say there are 26 alphabets, right? So if there are 26 alphabets, and then you just want 1, right, to fit there, then that fits into your 26 perm 1. I hope that makes sense. So you get your 26 perm 1. So that's 50. Okay. And now you have 2 numbers. Now you have 2 numbers, right? The lady says she remembers 2 numbers. That is 1 and 2. But then she does not remember the order. So since she does not remember the order, how do we arrange 2 things? We can arrange them in 2 permutations 2 ways. Right, so these are the 1, 2 she remembers. But then if she remembered the order, then this term will not be there. So to just look like this one, because this one she remembers the order. She didn't say she remembers A and she remembers S, but she says AS. So she remembers the order of this. But then she doesn't remember the order of the numbers. So we'll just do this. And then the last thing is we need our last number. What last number can we get? So from 0 to 9, those are 10 unique things. Then you can just pick one. So this is how this question would work. So you have to find 26 permutation 1 times 2 permutation 2 times 10 permutation 1. So this one, that will be 26 on what? 26 factorial on 25 factorial. Then that leaves us with 26. 2 permutation 2, that's what 2. And then 10 permutation 1, that's 10, so that's still 10. Right? So this time is 52, 520. So that gives us 520 ways. So that simply tells the police that they can put 520 cars, right, on their suspect list. So let's just try and see if we are. So maybe the car number, we can have one car number that looks like this, right? Or so all the possible car numbers will be put on whatever their list. So you can see that you can even switch these two because she doesn't remember the order. So you have, so these are all possible car numbers. So let's say when you keep writing all the possibilities, you write 520 numbers. So the police can say, okay, these are the 520 numbers we can deal with. And possibly if they go and they find that some of the cars are not in work and all of that, then they can keep narrowing down their possibilities to see who really the criminal is. So yeah, so that's just all for permutations and combinations and some real world applications. In the slides there are a lot of examples, a lot of solutions. But I hope this helps you in preparing for the IE and then for the examination. Okay, so thank you and have a nice day.